We're now going to look at a settled sewerage design example. We have to design a settled sewer to serve 10 compounds plus 2 future extensions. The average family size of the compounds is 24, and they have a water consumption of 70 litres per person per day. So we can calculate the peak flow from each compound as 1.5 times 10 to the minus 5 pW, and that works out at 0.025 litres per second. One of the 2 further extensions is for 10 compounds and the other for 20 compounds, and they discharge into the sewer at the point shown on this chart. On this chart we show our 10 stations, which we divided the sewer into, and vertically we're plotting the elevation of each station above the datum level of station 1. And we're plotting horizontally the horizontal distance from station 1. And this is the design procedure we use. We select sewer sections for hydraulic analysis on the basis of each section having reasonably uniform gradients or flows. Here we've chosen 9 sections, and the hydraulic calculations are given in this table. We have 10 stations, so therefore we have 9 sections, and our calculations are done in 10 columns, and I'm now going to describe each of these columns in turn. Column 1 is the station number. It's the number given to the point at which each section starts, commencing from the downstream end of the sewer. Column 2 is the station elevation, the elevation of each station above the datum, taken here as the elevation of station 1, and it has units of meters. Column 3 is distance, the horizontal distance of each station from station 1, again in meters. Column 4 is the elevation difference over the section, so that's the difference between the elevation of adjacent stations. Column 5 is the section length, so that's the difference between adjacent station distances. Column 6 is the average section slope, so that's column 4 divided by column 5. Column 7 is the number of connections served, and this is the cumulative number of compounds connected upstream of the downstream end of each section. Column 8 is the design flow. That's the peak flow in the section in litres per second, so that equals the number of connections served, given in column 7, times the peak flow per compound, which we have already calculated as 0.025 litres per second. Column 9 is the sewer diameter, the diameter in millimetres which we select as the designer for each section. And we have to realise at this stage that our initial choice may prove to be inadequate and the pipe size may have to be increased. Column 10 is the flow at full pipe, which is given by this equation. Q is equal to 2.4 times 10 to the minus 4, d to the 8 over 3, where d is the diameter given in column 9, times I to the half, where I is given in column 6. For example, for section 1, the flow at full pipe Q is equal to 2.29 litres per second. So going back to the table, we do the hydraulic calculations for each of the 9 sections, and then there are 2 things we must check. Firstly, to see if our initial choice of sewer diameter was adequate or not, and then to examine what happens at any critical sections. So looking first at the initial choice of sewer diameter, column 9, and if we look at the section between stations 1 and 2, our design flow is 1 litre per second, and the flow at full pipe is 2.29 litres per second. So the flow at full pipe is larger than the design flow, so this means that our choice of 50 millimetres for the sewer diameter was perfectly okay. However, in 2 sections, our initial choice of 50 millimetre diameter sewer is not satisfactory. These sections are between stations 2 and 3 and between stations 5 and 6. In both cases, the design flow is more than the full pipe flow, and so we must use a 75mm diameter sewer rather than 50mm. And then in both cases, the flow at full pipe in the larger diameter sewer is more than the design flow. So in these two sections, between stations 2 and 3 and 5 and 6, we found that the 50mm pipe was too small, and we had to use 75mm pipe instead. In both cases, it's worth noting, the 75mm pipe discharges back into a 50mm pipe. And this is not possible in conventional sewerage, but perfectly possible with settled sewerage. Now, this design example was done with an initial choice of 50mm sewer diameter, simply to demonstrate its hydraulic feasibility. In practice, we would use a minimum diameter of 75mm, as this would facilitate cleaning of the sewer should this ever be required. However, it's worth noting that in some schemes in the United States, 50mm has been used satisfactorily for many years. The second thing we have to look at are the critical sections. Flat sections, and there are none in this example, and the sections in which the flow is pressure flow. And here there are 3 sections, between stations 3 and 4, between stations 6 and 7, and between stations 9 and 10. And in these sections we have to avoid the wastewater backflowing from the sewer to the interceptor tank. This slide shows the hydraulic calculations table again, and the 3 sections under pressure flow. Taking the section between stations 6 and 7 as an example, we can calculate that the hydraulic gradient over this section is 0.012 and that it rises 0.89 metres above station 7, which is the upstream end of the section. First of all, we calculate the hydraulic gradient across the section of sewer when it's flowing just full. This is the equation for Q, which we've had before, and we rearrange this in terms of I. So, for example, for the section between stations 6 and 7, Q is equal to 0.9 litres per second, and that's given in column 10, and we've chosen D as 50mm, so I is calculated as 0.012 metres per metre. And then we calculate the maximum elevation to which the hydraulic gradient rises. So that's the hydraulic gradient, 0.012, times 74, which is the section length given in column 5, and that works out at 0.89 metres above the upstream end, which is station 7.